Hello everyone, welcome to Brain Blitz Audios. Today we're going to be looking at derivations with respect to the 12th chapter in the grade 12 syllabus for physics in CBSE. The chapter is atoms and this chapter has very few derivations. So we'll be able to complete all of that in just one video. So stay tuned for our channel Brain Blitz Audios and then check out more of these videos and others which will be uploaded soon. So, the chapter Atoms deals with the structure as well as the electrons of an atom. And in the next chapter, Nuclei, we'll be looking at more about the nucleus, protons, and radioactivity, etc. So, in the chapter Atoms, you have about 5 to 6 derivations, and that's it. You can complete the chapter. Physics is all about derivations, and if you can remember those, then you don't need to remember the formulae, and then you can use those derivations and formulae in order to solve most of the problems. So this is the first derivation that we'll find in the chapter Atoms. You need to find the expression for the distance of closest approach in Rutherford's experiment. So in Rutherford's alpha scattering experiment, he put an alpha particle through a gold sheet and then he found out his results. So an alpha particle traveling directly towards the center of the nucleus slows down as it approaches the nucleus at a certain distance r from the nucleus. The alpha particle comes to rest and its kinetic energy is completely converted in electrostatic potential energy. The distance r0 is called the distance of closest approach. Now let's derive the formula for distance of closest approach. So in order to derive that, we need to consider an alpha particle. So let's start writing that. So consider an alpha particle of mass m possessing initial velocity u when it is at a large distance from the nucleus. And this nucleus has an atomic number, say Z. Now, to find out the distance of closest approach, the condition that we use is that at the distance of closest approach, all of the kinetic energy, that is Ke of the alpha particle, is converted to what is known as electrostatic potential energy, or Pe. So kinetic energy Ke is written as half mv squared for any sort of particle, and the electrostatic potential energy, that is U, is represented as K times Q1 times Q2 divided by R, where Q1 and Q2 are two charges and R is the distance between them. So according to the given condition, we can write down the equation that is half mu squared is equal to 1 by 4 pi epsilon naught times Ze times 2e divided by r. Now, u is the initial velocity of the electron, and Ze is the total charge present in the nucleus. So we can represent charge by its quantized form, Q equals Ne, where E is the charge of a single electron. So in a nucleus, you have charge equal to Z number of electrons, and an alpha particle always has +2 charge. So it will be having +2e amount of charge. So Ze times 2e divided by r. Now 1 by 4 pi epsilon naught is the constant, which is k, so we'll substitute that as k later. Now what are we going to do is the right hand side will just multiply e together, so the right hand side becomes 2z e square divided by 4 pi epsilon naught r. And the left hand side stays the same, half mu square. So now what we're going to do is we're going to take r to the left hand side, and everything else on the left hand side comes over here. So the value of r is equal to 2z e square divided by 4 pi epsilon naught into 2 divided by mu square. 2 times 2 is 4, and then you have z e square divided by 4 pi epsilon naught mu square. So now what are we going to do is we're going to take 1 by 4 pi epsilon naught as k, so that will be equal, so the value of r will be equal to 4k z e square divided by mu square. And this is our final equation. The reason why I took it as k, because most of us know the value of k as 9 into 10 raised to 9. However, if you were to use 1 by 4 pi epsilon naught, then you'll have to substitute a lot more constants. So writing it as 4k z e square by 4 mu square is more appropriate and easier to calculate. So that is the expression for the distance of closest approach. Now let's look at the next expression. Next derivation is for Bohrs quantization condition of angular momentum. This derivation requires you to remember concepts of the previous chapter. So in the previous chapter, we know that matter can be divided into radiation, that is wave nature, and mass, so that is particle nature. So you have both wave nature as well as particle nature for matter. This was the quantum theory. So the wave nature was represented by the formula n lambda is equal to 2 pi r, and the particle nature was represented by the formula L is equal to mvr, where L is angular momentum, lambda is the wavelength. So in order to solve this question, we also need to find out the de Broglie wavelength. So the de Broglie wavelength is represented by the formula lambda is equal to h by mv. So these are the three formulas in which we're going to use. So first things first, we have de Broglie's formula, that is lambda equals h by mv. So what we're going to do is we're going to convert mv in terms of h. So mv on the left side will be equal to h divided by lambda. That is the first thing to do. Next, remember that we had the equation n lambda is equal to 2 pi r. We're going to write it in terms of lambda, so lambda is equal to 2 pi r divided by n. And we're going to put both of these values into the third equation, that is L equals mvr. Now mv is h by lambda times r, and lambda we can write that as h divided by 2 pi r divided by n, and r is in the numerator. So now you have nhr divided by 2 pi r. Both r's get cancelled, so now you'll get angular momentum L equals nh by 2 pi. So if you were to write this down in the form of a sentence, then what this quantization condition essentially means is that the angular momentum of an electron is the integral multiple of h divided by 2 pi. L equals nh divided by 2 pi. This is the Bohrs quantization condition. Now, the next expression deals with Bohr's theory of hydrogen atom. So we're asked to find out the radii of permitted orbits in Bohr's theory of hydrogen atom. So now we consider an electron revolving around a nucleus, and it has a radius, say r. And you need to find out the value of this radius for Bohr's stationary orbits. So according to Bohr, the centripetal force for the revolution, that is the circular motion of an electron, is provided by electrostatic force of attraction. So as you can see, the nucleus is positively charged and the electron is negatively charged, so therefore they attract each other. And this attraction gives you the necessary centripetal force for the electron to revolve around the nucleus with a specific orbit. And using this condition, that is centripetal force equals electrostatic force of attraction, we can write out the formula mv squared by r equals the formula for electrostatic force, that is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Here q1 and q2 are e, so that means q square by r square, so e squared by r square is our formula for this equation, for this condition. So now we're going to simplify the denominator, so r gets removed from both ends, so you have mv square equals 1 by 4 pi epsilon naught e square divided by r. Now we consider this as our first equation. Now remember from our earlier equation that angular momentum L, which was equal to mvr, can be also represented as the integral multiple of h by 2 pi. So mvr equals h by 2 pi. So if you take v on the left hand side, you get nh divided by 2 pi r times m. This is considered as equation 2. Now what are we going to do? We put the value of equation 2 in equation 1. So in equation 1, you had mv square equals 1 by 4 pi epsilon naught e squared by r. So the formula now becomes m into nh divided by 2 pi rm, the whole square, equals 1 by 4 pi epsilon naught e squared by r. So the left hand side becomes m times n square h square divided by 2 square is 4, pi square, r square, m square. And the right hand side is 1 by 4 pi epsilon naught e squared by r. So over here you can cancel out a lot of terms. For instance, you can cancel out 4. They're on the denominator on both sides. Pi also gets cancelled. One of the r's gets cancelled. And you have one of the m's also getting cancelled. So the equation that now you get is n square h square divided by pi mr is equal to e squared divided by epsilon naught. So therefore, now you can rearrange the terms, so r goes on one side and all of the other terms go on the other side. So you get n square h square epsilon naught divided by e square pi m. So r equals n square h square epsilon naught by e square pi m is the right answer. Is what we get. And you can rearrange that as epsilon naught n square h square divided by pi m e square. Both are basically the same. Now, when n equals 1, that means when you are having to find out the radius of the first orbit, then r1 will be equal to e naught h square divided by pi m e square times 1 square, which is 1. So experimentally, we found out that the value of r1 is 0.53 into 10 raised to minus 10 meters, or 0.53 angstroms. So this is the value of r1. So therefore, you can find out the value of r, or say rn, as the value of r1 times n squared, because basically this constant is multiplied with n squared in order to get the value for the radius. So it makes sense to write that down as r1, because then it will be a whole lot easier just to put in 0.53 instead of putting all the constants there together. So you can use this formula for your calculations if you know the value of n and you need to find out the radius. So that gives you the radii, the permitted radii in Bohr's stationary orbits. The next thing you need to find out is to find the expression for velocity of electrons in Bohr's theory of hydrogen atom. So, velocity of electrons. In order to find the velocity of electrons, we again use the formula for angular momentum. The relation that we used earlier also was mvr equals nh by 2 pi. And from there you can get v as nh divided by 2 pi m into 2 pi r. Now let's write it like that for now. Now, we also know that, so we know from the previous derivation that r equals epsilon naught n square h square divided by pi m e square. This is the value for r. Now, what we're going to do is we put r, value of r, in the equation for velocity. So now what you get is v equals nh divided by m times 2 pi times, and then you write the formula, epsilon naught n square h square divided by pi m e square. So in order to solve this question, in order to further go on with this derivation, what we're going to do is we're going to take the denominator pi m e square to the numerator, because what happens is you have 1 by pi m e square, which is the reverse of, which is just the same as pi m e square. So what we're going to do is we're taking pi m e square to the numerator. So velocity is nh into pi m e square, that's the numerator, and the denominator is 2 pi m times epsilon naught n square h square. So n gets cancelled, h gets cancelled, pi gets cancelled, m gets cancelled. So the value for velocity is e square divided by 2 epsilon naught n h. So this is the formula to find out the value of velocity. Now, in order to find that, we used angular momentum, and we also used the previous derived formula for radius, and we put in those values and we got the answer for velocity in Bohr's theory of hydrogen atom. Now we need to find out the energy of an electron in Bohr's theory of hydrogen atom. So an electron is revolving around the nucleus. So this is the situation. So there are two energies at play when an electron is revolving around the nucleus. So that is kinetic energy of the electron and potential energy of the electron. Now, all of us know that kinetic energy can be represented as half mv squared. Now, in an earlier derivation, we learned that mv squared is equal to 1 by 4 pi epsilon naught e squared divided by r. This was what we got when we were solving for radius of an electron. So we can still use that relation here. So what we're getting is kinetic energy will be equal to half into 1 by 4 pi epsilon naught times e squared divided by r. So that is equal to 1 by 8 pi epsilon naught e squared divided by r. So this is the value for kinetic energy of an electron. Now, to find the potential energy U is represented as 1 by 4 pi epsilon naught Q1 Q2 divided by R. So in this situation, we have the potential energy is equal to 1 by 4 pi epsilon naught minus E the whole square divided by R. That is the product. So we have minus E squared divided by 4 pi epsilon naught R as the value for potential energy. In order to find the total energy of any system, we add the kinetic energy and the potential energy. So in this case, you have 1 by 8 pi epsilon naught E squared by R, which we can write down as E squared divided by 8 pi epsilon naught R minus of E squared divided by 4 pi epsilon naught R. So now what we're doing is we're taking 1 by 4 pi epsilon naught R outside. So you basically have E squared by 2 minus E squared. So that becomes so that we can further write as 1 by 4 pi epsilon naught R E squared minus 2E squared E squared by 2 minus 2E squared by 2. So now we get 1 by 4 pi epsilon naught R, and inside the bracket it'll be minus E squared by 2. And on multiplying the 2, the total energy that you get is minus E squared divided by 8 pi epsilon naught R. So this is the value for the total energy. But we're not finished yet. What we're now going to do is we're now going to substitute the value of R. Since R is equal to epsilon naught n squared h squared divided by pi m E squared, we're going to substitute that value here. So minus E squared divided by 8 pi epsilon naught. Then inside the bracket you have epsilon naught n squared h squared divided by pi m E squared. So the total energy now becomes minus E squared times pi m E squared divided by 8 pi epsilon naught times epsilon naught n squared h squared. So over here you can only cancel out pi, so you do that, and therefore the equation that you now get is minus m times E squared becomes E raised to 4 divided by 8 and then epsilon naught the whole square, because there are two of them multiplied. Then you have n square and h square. So minus me square divided by 8 epsilon naught square into n square into h square. But are we done yet? No, we're not. The total energy, let's write this as E. The total energy for an electron in the first orbit is minus 13.6 electron volts. And that will be equal to minus me raised to 4 divided by 8 epsilon naught square h square times 1 by 1. That means just 1. So the constant would now equate to minus 13.6 electron volts. So energy for an electron in the nth orbit can be written down as minus 13.6 divided by n square electron volts. And again, this is easier to calculate. The final equation would be minus me raised to 4 divided by 8 epsilon naught square n square h square. But it's easier to find out all of these constants first in the first term, so that you get minus 13.6 and use that 13.6 to find out the value for the energy in the nth orbit. So that's what we did. So En will be equal to minus 13.6, that is E1 divided by n square electron volts. This is the final derivation of this chapter. We need to find the general formula for spectral series of the hydrogen atom, the general expression for spectral series of hydrogen atom. So what is spectral series? In an atom, when an electron jumps from higher energy level to a lower energy level, the difference between the two energy levels is emitted as radiation of a particular wavelength. This radiation is known as a spectral line, and for each element it's present. The wavelength of spectral line depends on the energy associated with the two energy levels. So the spectral wavelength would depend on the two energy levels between which the transition of an electron takes place. So we're going to find out exactly what is the relation between wavelength and the spectral series. So the energy levels and the wavelength are related together in order to find the formula for a spectral series of hydrogen atom, and that is what we're going to find out. So the first thing that we need to write is let EI and EF be energies of an electron in the initial stationary orbit and final stationary orbit. Now the initial stationary orbit has the principal quantum number Ni. The initial stationary orbit has a principal quantum number Ni, and the final stationary orbit has a principal quantum number Nf. So the condition for spectral series was when an electron jumps from Ni to Nf, the difference of the energy associated is given out as the wavelength. So when an electron jumps from the initial stationary orbit Ni to the final stationary orbit, that is Nf, in the conditions that Ni is greater than Nf, the difference of energy is given by EI minus EF is equal to h nu. Now the reason why we put h nu is because radiation is being emitted when this difference happens. So when the electron is moving from initial to final stationary orbit, there is a release of radiation, and therefore because of that we write radiation, the energy of the radiation, as h nu. So in order to you know, calculate the exact energy difference and the frequency at which it occurs, we put the initial energy as using the formula minus m e raised to 4 divided by 8 epsilon naught h square ni square. And for the final energy of the electron, we again use the same formula. Instead of ni, it is just nf, epsilon naught h square nf square. So since h nu is given as ei minus ef, that will be equal to minus m e raised to 4 divided by 8 epsilon naught h square ni square minus m e raised to 4 divided by 8 epsilon naught h square nf square. So over here you can take m outside, e raised to 4 outside, and you can take 1 by 8 epsilon naught h square outside as well. So you have minus 1 by ni square plus 1 by nf square, which we can further write it as m e raised to 4 divided by 8 epsilon naught h square 1 by nf square minus 1 by ni square. Now the constant here, which is m e raised to 4 8 epsilon naught h square, is not complete because you also have a constant on the left hand side, which is h. So nu, which is frequency, can be written down as m e raised to 4 divided by 8 epsilon naught h cube, and then you have 1 by nf square minus 1 by ni square in the bracket. So you have frequency given here. And another formula for frequency is the speed of light divided by the wavelength. Now, this is the same as, time is equal to distance by speed, so 1 by time is equal to speed by distance, and frequency is 1 by time. So therefore, c divided by lambda will be equal to m e raised to 4 divided by 8 epsilon naught h cube 1 by nf square minus 1 by ni square. And in order to express this relation in terms of only wavelength, we take c to the right hand side, so you have 1 by lambda equals m e raised to 4 divided by 8 epsilon naught c h cube, and then inside the bracket you have 1 by nf square minus 1 by ni square. So this constant that now we have got when 1 by lambda is on the left hand side, this constant here is known as the Rydberg constant. So m e raised to 4 divided by 8 epsilon naught c h cube is equal to Rydberg's constant, which we represent as RH, and that is equal to 1.09678 into 10 raised to 7 meter inverse. So when we put this value in our equation, then 1 by lambda is equal to let's write RH times 1 by nf square minus 1 by ni square. So this is the final equation with respect to spectral series. From here onwards, you just need to substitute the value of nf with 1, 2, 3, or 4. So if you have nf as 1, you get Lyman series. If you have nf as 2, you get Bohrs series. If you have nf as 3, you get Paschen series. For nf is equal to 4, you get bracket series. For nf equals 5, you get the fun series. And each of these series have their own spectral, properties, and also properties with respect to the wavelength, etc. So this is the basic equation for finding out which spectral series the spectral line belongs to. So that basic equation is 1 by lambda equals RH times 1 by nf square minus 1 by ni square. Now that concludes the whole chapter, atoms and its derivations. So we hope you found this chapter interesting. For more of such useful videos, don't forget to subscribe to our channel, which is Brain Blitz Audios. So derivations are pretty important in board exams, so therefore studying them is also as important as practicing numericals. So we hope you found this video useful. And so until the next episode, take care, stay safe, bye-bye for now.